Imagine looking into just a totally serene, predictable aquarium. You know the kind I mean, right?
Oh, yeah, definitely. The classic setup.
Right. So you are expecting the usual miniature landscape in there. You've got the clean gravel, maybe a nice piece of driftwood, and those delicate wispy green ferns just sort of swaying gently in the filter current.
Yeah, the stuff that just looks really peaceful.
Exactly. But picture this. Instead of a delicate underwater fern, you look down and see this cluster of disembodied, eerie green fingers just reaching down into the water.
Like a bunch of alien hands or something.
Yes, it looks way less like aquatic flora and more like some bizarre underwater art installation. And well, today's custom deep dive is about exactly that.
It really is a total mind bender of a plant.
It is. We are looking at a genuine biological anomaly that completely shatters our expectations of what a plant should even be. We are exploring the Nymphoides aquatica, which is commonly known as the banana plant. And we're looking at it through the lens of this really fascinating Fishkeeping journal entry. It was published on June 3rd, 2026.
Yeah, and it really is the ultimate botanical double take, honestly. The author of our source material, who is this veteran fish keeper known just as Ang, documents this whole encounter.
Right, in that specific entry.
Exactly. It's an excerpt titled Notes on Fishkeeping, Part 266. And honestly, that detail right there, the Part 266 bit, is crucial context for everything we're going to talk about today.
Oh, 100%. Because, I mean, think about what writing 266 entries on fish keeping actually implies.
You've basically seen it all.
Right. If you are keeping a journal going for that long, you are deeply familiar with the ecosystem. You know the standard nitrogen cycles. You know the typical aquatic plants that just look like, land plants holding their breath.
Yeah, you become completely immune to the mundane stuff.
Exactly. So an aquarist at that level is totally conditioned to the subtle variations of this very specific closed environment.
So when someone like Ang dedicates a whole entry to calling this plant a botanical curiosity and says it's one of the most unique things they've ever seen, I mean, that carries some serious weight.
It really does.
It means this organism isn't just slightly unusual. It is fundamentally disrupting the expected mechanics of its whole environment.
And Ang's visual description of this disruption is just incredibly evocative. Like, if you were to walk up to this tank suspended right there in the lower half of the water column, you wouldn't see a normal stem plunging into the gravel.
No, not it.
You would see this thick, tightly packed cluster of tubular, really fleshy green shapes. Ang notes that it looks exactly like a bunch of completely unripe green bananas hanging out in the water.
Which is such a strange image for an aquarium.
It is.
Yeah.
Or, even more unsettling, Ang says it looks like a cluster of fleshy fingers.
Right, which is just a profound visual disruption because it completely defies our mental schema,
Yeah, it totally messes with what we expect.
Because we are accustomed to a very specific architectural hierarchy in nature. Plants, especially aquatic ones, usually communicate this sense of delicacy. They flow with the water.
They drift.
Exactly. So seeing a dense, thick cluster of fleshy shapes hanging rigidly in the mid-water, it completely contradicts that whole delicate aesthetic.
Okay, let's unpack this. Because if you or I, or really anyone taking just a casual glance at this tank, saw a cluster of anything at the base of a plant, our brains would instantly categorize it.
Oh, absolutely. We put it in a neat little box.
Right. We would look at those green banana-like fingers, and, well, when a casual observer looks at this, they're going to assume those banana fingers are just a very weird root system, right?
Yeah, I mean, it is a completely logical deduction based on basically every other terrestrial or aquatic plant we interact with.
Because roots can be gnarly and strange, so it's just the logical default.
Right. But what's fascinating here is that the source material reveals that our instinctual assumption is entirely wrong.
Wait, entirely wrong?
Completely. And Gang explicitly notes that while these structures are easily mistaken for roots, they actually serve an entirely different biological mechanism. They're actually fleshy tubers.
Huh. Fleshy tubers, which honestly sounds incredibly counterintuitive for a submerged aquatic plant.
It really does.
Because when you say tuber, my mind instantly goes to, like, a potato.
Yep, the classic spud.
Right. A dense, starchy block buried deep underground in the dark soil, hoarding energy. It's hard to reconcile that heavy, underground concept with a plant suspended in a fish tank.
And that contrast right there gets to the very heart of the plant's survival strategy. Let's think about the function of a tuber compared to a traditional root system.
Okay, lay on me.
So a standard root system is active,
Yeah.
right? It is a foraging network. It constantly spreads out, mining the surrounding soil or gravel, actively hunting for micronutrients day in and day out.
It relies entirely on the quality of its immediate environment.
Exactly. It's tied to the local real estate.
So it's living paycheck to paycheck, essentially. Whatever the gravel provides that day, the root has to just absorb.
Precisely. But a tuber operates on a totally different economic model. A tuber is essentially a biological battery.
Oh, wow, a battery.
Yeah. And the specific purpose of these unripe banana structures on the Nymphoides aquatica is entirely dedicated to long-term nutrient storage.
So instead of just anchoring into the dirt like a normal root and relying on the local real estate for its daily meals, it's like the plant is carrying around its own built-in, fleshy underwater pantry.
That is exactly the mechanism at play. It's an underwater pantry, and it provides this profound independence for the plant.
Because it doesn't need the gravel to be perfect.
Right. If the substrate is nutrient poor, or if the water conditions fluctuate wildly, which happens frequently in natural aquatic environments, the banana plant doesn't immediately suffer.
Because it has its own reserves.
It has its own lunchbox. It has these dedicated fleshy reservoirs hanging right there in the water, loaded with all the necessary fuel to sustain itself and initiate new growth, regardless of what the immediate surroundings are doing.
Man, that evolutionary independence is brilliant, but it immediately introduces a massive physical problem to my mind.
Oh, what's that?
Well, if I'm packing a biological lunchbox full of dense nutrients, like if I have a cluster of thick, fleshy tubers packed with starch and energy, that has to be heavy, right?
You would think so, yeah.
I mean, a real banana sinks. A potato definitely sinks. So if this plant is hoarding all this dense material in its base, gravity should be the absolute boss of the situation.
It's a very logical assumption.
It feels like the sheer weight of that pantry should be dragging the entire plant down, burying it flat against the gravel like a rock. How does it not just sink and rot in the mud?
And that is the exact logical friction that makes the Nymphoides aquatica such an engineering marvel. You are applying the standard physics of density, which makes total sense.
Right, because heavy things go down.
Exactly. We associate thick, fleshy structures with weight and a downward trajectory. But Eng's notes reveal a staggering, totally counterintuitive reality about how these specific tubers interact with the physics of water.
Let me guess. They've figured out some weird way to cheat the physics.
Well, they don't cheat physics, they actually weaponize it. Despite looking incredibly dense and heavy, like a thick, solid bunch of bananas, the source reveals that these tubers are actually buoyant.
Wait, buoyant?
Yes, buoyant.
As in they actively float. The heaviest, thickest-looking part of the plant wants to go up.
Yes, they possess upward lift. They are not dead weight acting as a sinker. They are actively working against gravity.
Okay, my brain is slightly breaking trying to visualize the mechanics of this.
It's definitely weird to picture.
Because, wait, here's where it gets really interesting. If they are buoyant pantries, wouldn't the whole plant just rocket to the surface and pop out of the water like a cork?
You'd think it would just float away, right?
Yeah. If you tie a bunch of life preservers to a plant, how does it stay oriented in the tank? How does it even manage to grow if its base is constantly trying to float away?
To understand that, we really have to look at the energy economics of plant growth, especially in an aquatic environment.
Okay, break that down for me.
Well, think about a terrestrial plant, a tree, for example. To get its leaves to the sunlight, it has to spend a massive amount of biological energy producing wood or lignin.
Right, it has to build a trunk.
Exactly. It has to build a rigid, thick trunk capable of fighting gravity and pushing the foliage upward into the sky. It is an incredibly expensive architectural strategy for the plant.
Because air offers no support.
Yeah.
The plant has to hold its own weight up entirely.
Exactly. But water is a dense medium. It actually offers support. So the banana plant realizes it doesn't need to waste energy building a rigid, woody trunk to reach the sun.
Oh, I see where this is going.
Right. Instead, it uses the natural buoyancy of its own nutrient storage. The source text explains that from these floating bananas, the plant naturally develops what are called petioles.
Petioles, which are essentially the stalks connecting the base to the leaves, right?
Right. But crucially, the text specifies these are long, thin petioles. They aren't thick or rigid. They don't have to be.
Wow, I see the mechanics now. It's like a reverse anchor.
A reverse anchor, yes.
Instead of dropping heavy weight to hold a structure rigid against the current, the plant is basically inflating a biological life vest.
That's a great way to put it.
The upward lift of those buoyant tubers naturally pulls the whole operation upward, creating tension, so the plant doesn't have to push those thin strings up a foot. The tubers are effectively towing them toward the light.
Biological life vest is just the perfect way to articulate the physical mechanism here.
It makes so much sense when you picture it like that.
It does. The buoyancy isn't an accident the plant is fighting. It is the very engine of its vertical development. It is hitching a ride on its own flotation device.
Which has to save the plant a tremendous amount of structural energy.
Oh, absolutely. Why build a stiff trunk when you can just let the upward lift of your own pantry pull your thin lifelines toward the sun?
That is just spectacularly efficient engineering. But, you know, it completely flips the visual script for me.
How so?
Well, if we follow those long, thin strings being towed upward by the life vest, where exactly are they going?
That is the big question.
Because if the bottom of this plant is this weird engine room that looks like eerie alien fingers, I have to assume the foliage it produces is going to be some terrifying, carnivorous-looking monstrosity at the top.
You'd expect some kind of swamp monster plant.
Right. Does it produce more fleshy bananas higher up? Like, what does this thing look like when it finishes growing?
Well, the destination of those petioles reveals the ultimate twist of this plant's biology.
Oh, I love a twist.
They have a very specific endpoint in mind, and they do not stop in the mid-water. The text points out that those thin lifelines are driven upward until they reach the absolute surface of the water.
Okay, all the way to the top?
Yep.
And when they finally break the surface, the transformation is dramatic. And it is the exact opposite of a carnivorous monstrosity.
Really?
Yeah. Once those long petioles hit the top of the water tank, the foliage they produce is explicitly described in the source as looking exactly like a lily.
A lily pad? You're
I'm
kidding.
completely serious. A classic, delicate lily pad resting flat on the surface of the water.
Let's synthesize this for a second. Because the sheer biological duality of this organism is staggering.
It really is a masterclass in split identity.
Think about the complete picture we just built here. If you are just a casual observer looking down at the surface of the aquarium, or I guess if you are out in nature looking at the top of a pond, what you see is the absolute universal symbol of calm, peaceful nature.
A quintessential pond aesthetic.
Exactly. An elegant, delicate, incredibly commonplace lily pad resting gently on the water, soaking up the sun. It is the height of predictable, meadow-like aquatic scenery.
It is the picture of tranquility. It perfectly matches our conditioned expectations of what a water plant should look like.
But that tranquility is a total masquerade.
A complete illusion.
Because to support that perfectly normal, elegant surface facade, there is a deeply bizarre, highly engineered support system hiding completely out of sight.
Way down in the dark.
Down below, lurking in the depths of the tank, is this surreal cluster of fleshy green fingers. An underwater battery pack that looks heavy but actively floats, acting as a reverse anchor to tow the plant to the light.
It's wild when you put it all together.
It is. It is a completely alien engine room powering a totally conventional roof. So what does this all mean?
Well, that stark contrast explains exactly why Ang felt so compelled to document this specific organism after 266 entries.
Right, why this one stood out so much.
The Nymphoides aquatica is a study in brutal efficiency hidden behind conventional beauty.
Brutal efficiency, I like that.
Because the lily pad shape at the top isn't just pretty. It is the mathematically perfect shape to maximize surface area for solar collection without being torn apart by surface tension.
Form meeting function perfectly.
Exactly. And the fleshy tubers at the bottom aren't just weird for the sake of being weird. They are a highly evolved combination of nutrient independence and energy-saving upward lift.
It really highlights how nature doesn't care at all about our aesthetic expectations.
Not even a little bit.
It only cares about survival mechanisms. It solves the problem of storing long-term food and the problem of reeking the sunlight without wasting energy on a thick trunk simultaneously.
And the result just happens to look like an incredibly strange art project.
It really forces the observer to question their assumptions.
Oh, absolutely.
You assume roots anchor a plant, but these float. You assume thick, fleshy structures sink, but these are buoyant. You assume a bizarre base means a bizarre canopy, but it produces a classic lily.
It reminds us, as Ang so astutely observed, that true botanical curiosities aren't just visually strange.
Right, they're functionally strange, too.
Exactly. They operate on an entirely different set of logical principles than the ones we are used to.
It's just a phenomenal journey from the bottom of the tank to the top.
It really is.
To recap the incredible architecture we've explored today, we started in the depths with a structure that perfectly mimics weird, heavy roots.
But which are actually anything but roots.
Right. Through closer inspection and understanding the physical mechanisms at play, we revealed them to be floating, nutrient-packed biological batteries.
Those fleshy pantries shaped like unripe bananas.
Yes, the ones that act as life vests. And from there, we followed those highly efficient thin stalks as they used that very buoyancy to cheat the energy costs of gravity.
Hitching a ride all the way to the top.
Hitching a ride to the top. And finally, we arrived at the surface, witnessing how that bizarre alien machinery culminates in the serene, completely familiar beauty of a lily pad resting calmly on the water.
It is a brilliant testament to the complexity hiding in plain sight, and it was captured perfectly in just a few observant notes from a veteran fish keeper.
It really proves that even in a controlled, artificial environment like an aquarium, nature will always find a way to surprise us with its hidden mechanics.
It never runs out of tricks.
Absolutely. And as we wrap up this deep dive, I want to leave you with a final thought to ponder as you step back into your own environment today.
Something to chew on.
Yeah, we have spent this time marveling at the dual nature of the banana plant, how it presents this beautiful, serene lily pad on the surface, a face of total elegance and normalcy, while secretly being powered by a highly complex, slightly bizarre, and entirely unseen support system of floating green fingers hiding in the depths.
It's a profound and highly functional masquerade.
Exactly. So what other things out there operate on this exact same principle?
That's a great question.
Whether it is in the natural world and the human-made systems we interact with, or even in our daily lives, what else presents an elegant, simple, entirely familiar face to the world while secretly relying on a deeply complex, bizarre, or even chaotic support system churning just beneath the surface?
You know, it makes you look at everything a little differently.
It really does. What beautifully simple user interface in your life is actually powered by an alien engine room?
I'll definitely be thinking about that.
Thank you so much for joining us on this custom deep dive today. Keep questioning the surface of things, look for the hidden mechanics, and always stay curious.